So tangent lines are a huge part of the AP exam, but in order to be able to do a tangent line, you need to understand a derivative. So a tangent line and a derivative go hand in hand in the sense that the tangent line comes from an original line, finding its rate of change, and using that rate of change to find the slope at a particular point that represents that tangent line. So that all goes back to our beginning days where we talked about limits, we talked about the definition of the derivative. The definition of the derivative itself says that the derivative of a function f is represented by that limit. The f of x plus h represents the change in that derivative from point x to point h. We learned that we made h infinitely close to 0 so that we can find
the guidance office. Caitlin Woods, Jalen Root, Mia Reddix, and Lauren Urbanek. Thank you.
So we can find the derivative at that point. So now we know what the derivative of this is. If you had to work it out by hand for the definition of the derivative, I worked it out for you, kind of as like a nice review. But what we're going to, reiterate and reevaluate is, okay, that's the definition of the derivative. That's my derivative. F prime of x as 6x squared represents the slope of the tangent line for any point x. So f prime of x represents the slope of the tangent line for any point x. And then what happens is we say, okay, well, what is the equation of the tangent line when x is 2? Well, now that adds to the components of this, which is that you need to be able to find f of 2 and f prime of 2, and then plug in the point slope. Or it might be approximate f of 1.01. And then we'll use 1 to find the equation on the tangent line, then plug in. Our derivatives have 5 basic rules, and then a slightly more complicated difference rule. So the product of two differentiable functions is always another differentiable function. So that's one of those statements you'll hear me say. The product of two differentiable functions is always another differentiable function. The product rule says if you want to find the derivative of f of x times g of x, then you have to know your product rule, which is first times derivative of second plus second times derivative of first. The quotient rule is our hi-ho, it's off to calc you go, which is ho-di-hi minus hi-di-ho all over ho-ho. If you were to look at that in terms of f and g, so if I wanted to do the quotient rule for f of x over g of x, then that would look like d dx of f of x over g of x, which would be di minus I do all over. And it's important to understand that variation because they love tables. And if you had tables, then if you don't know the rule in terms of function notation, not being able to plug into a table is much more difficult. So again, the ODI minus IDO is great if you're saying it and you have functions, but if you have tables and your tables are f of x and g of x or v of t and p of t, then you have to truly understand the definition of the derivative for quotient rule in terms of functions. And that's the function equation. Composite functions are a fancy way of saying chain rule. Chain rule composites. I'm teaching composites in algebra 2 right now, and it's hard for me to be like, the chain rule in calculus. Because I know how important composite functions and understanding them are, because the chain rule is a function composition. It says we take the derivative of the outside function, keeping the inside function the same, then multiplying by the derivative of the inside function. And if you have another function within that function, then you do it again. Square roots are the most common chain rule function. The square root itself is the outside function. The inside function is that 2x cubed plus 5x. And then what happens is we have to also take into account domain. So is this function differentiable on the domain all reals? Well, if you weren't sure, what could you do? You would have to say, okay, what's under the square root for the original function has to be greater than or equal to 0. On our derivative function, the denominator can be 0. But the domain of the original would come from this, which again, go backwards in time. That's a creation of a number line, right? So this right here will always be positive because anything squared is positive. So now your domain, if you have x out in front, if x is -1, it's -1 times anything positive going to be greater than or equal to 0? No. So my domain, this part doesn't matter because it's always positive. My domain is coming from the idea that x must itself only be positive. Do you see how I kind of worked that though? Because at first you're looking at the cubic and you're looking at the 5x and you're like, oh, maybe. But the understanding for me would be, well, anything cubed can be positive or negative, and I can't have a negative, so negative. Do you remember how to take an answer like this and find its extrema? Because that's what we're going to go to probably tomorrow. And throughout the rest of the week is, okay, can you take this and find its extrema? So that's the points where top equals 0, bottom equals 0. Those are our critical points, which are potential extrema. I feel like integration reminded us of trig derivatives. Integration reminded us of our trig derivatives. Integration reminded us of exponential and log derivatives. So again, these are your basic rules. I have a cheat sheet that's going to have all of this on it. but like for tonight's homework, they're kind of all compacted in this pattern. Since the derivative of a function represents the slope of that function, this is what I was getting to. We really have derivatives and tangent lines coming back into play. A derivative at a point represents the instantaneous rate of change at that particular point. The average rate of change represents the slope using 2 points. That's our old slope formula. So a derivative represents instantaneous rate of change. So if you want to put like dy dx in there to remind yourself, average rate of change is your f of b minus f of a all over b minus a. AKA change in y over change in x. If you're given f of x at some point, then if you want to find the equation of tangent line, you have to find your derivative at f of a, and then plug in the point slope for it. Again, hinted at that earlier with that 6x squared problem. So these are really like the practice problems we're going to do. I'm going to give you another worksheet. This is kind of just like, hey, here's all the rules, all their ideas. So this is kind of like a made up AP question. Like this is not a past exam question. But it says the number of students with the flu is given by the function g, where g is people and t is time. Let t equals 1 represent the day of the first day of the month. Below is a graph of g along the tangent line on day 10. So at day 0, we have about 250 people with the flu. On day 10, we have 648, and on day 20, we have 1,682. So it says find the value of g of 20 minus g of 10 over 20 minus 10 using correct units. So that would represent an average rate of change. So using that context and using that idea, what would part A represent, and explain that in its meaning? So again, if you're taking 20 minus 10 in terms of that problem, g of 20 represents the number of people with the flu on day 20. So g of 20 would be 1,682. G of 10 would be 648 over 20 minus 10, which is 10. So that's 1,034 over 10. So 1,034 over 10. We'll just pull back a decimal so you can kind of get it as a decimal if this was a non-calculator. And that would be 103.4. So what that means is that that represents a slope, right? So the slope is positive. If you have a positive slope, then it is increasing. So we would say that the number of students with the flu is, and again, keyword, increasing at, and what did we call this? An average rate of 103.4 people or students, whatever we're going to use, per day. Oh, and then here's the big part. What days were we looking at? Instantaneous is on a particular day. Average is on an interval. So it is the number of students with the flu is increasing at an average rate of 103.4 people per day from day 10 to day 20. Because the average rate would be different if I did day 5 to day 9. The average rate would be different if I did day 10 to day 12. So it's very important that you understand in that explanation that you put the days from which it is occurring. So part A would probably be a 2-point part problem on AP exam. The 103.4 would get you the first point. That sentence would get you your second point. Set up an expression involving a limit that would find the instantaneous rate of change in the number of students with the flu on the 16th day of the month. So this is our definition of the derivative problem. Our limit, and again, you can set this up either way, right? This is the formal definition of the derivative. If I do limit as h approaches 0, that's the formal definition of the derivative, and that would be over h, right? The first part of the function represents the function and its change. The second part represents the derivative that we are finding at that particular point, right? So we would want g of 16 plus h minus g of 16. Because in the definition of the derivative, that g of 16 at the end represents what we are finding the derivative at. You can also do this using the limit with the alternate form of the definition of the derivative, right? So the alternate form starts with what you are finding the derivative at. So that's when you do g of 16 or g of t. It really doesn't, the order doesn't matter as long as your bottom part matches, right? So you're finding the limit, and in this case, it's t. So it'd be the limit as t approaches 16 of g of 16 minus g of t, or you could have written g of t minus g of 16. Like I said, it just depends on what you do in your denominator then. So this would be t minus 16, or this would be 16 minus t. The limit would be to 16 either way. It's just whichever way you want to do the other part. Both will work. Both will give you that same. Now, we don't have a function for t. We have a graph, but we don't have an actual function. So it says estimate the instantaneous rate of change. It says estimate because we don't have a function. So that's where we made our tables back in the day, and we tried to get really, really, really close to g of 16. So estimate the instantaneous rate of change in students with flu on the 10th day of the month. state your answer clearly and explain in a sentence how you got it. But we only know 2 points. Go back up to that graph. We know 2 points. We know 10, 648, and 20, 1682. Where the 20, 1682 is on the original curve. And then we know 10, 648, and 20, 1267. Well, 20, 1267 is on my tangent line. So if you want to know the estimated rate of change using that tangent line at 10, 648, we need to use the 20, 1267 to find the slope. Because we know those 2 points are on the tangent line, which means they can give me the approximation of the slope of the tangent. So again, the average rate of change and the instantaneous rate of change would have the same units. Average rate of change and instantaneous rate of change will have the same units. But obviously the functional values are not the same. So what does that mean? It means that we are saying the instantaneous rate of change, or the number of students with the flu on the 10th day, is changing at a rate of 61.9 students. So still increasing, but now it's increasing on the 10th day of that, not on the interval. So how did we get that answer? They're not going to ask you how you got your answer in the AP exam. But the way we got our answer was kind of what I showed you from the graph, is that we found the slope, but we didn't find the slope of the curve, we found the slope of the tangent.